G'day YouTube, welcome back to the VK8 FOAS YouTube channel. It is Sunday the 12th of May 2024 and today we are going to be covering the topic of Iridium satellite decoding. This is a subject that seems to be trending somewhat among my viewers at the current time because I've observed a sharp increase in emails and comments on my videos asking about it. So this video will serve as a comprehensive guide on setting up an Iridium satellite ground station and how to navigate the software decoding tools in Linux. I'm not really sure why I'm making this tutorial anyway, as the king, Aaron from the SEMA Executor YouTube channel, has extensively covered this topic on his YouTube channel already. However, a few of my video viewers complained that they couldn't follow along with his Iridium videos. You have to understand that Aaron is so high level and intelligent with his skills that it's probably near impossible for him to lower himself to the level of peasants like me and my viewers. Just kidding, I know you guys aren't peasants. So without further ado, I have my obligatory video recording beer here. And we'll get into it, shall we? So what exactly is Iridium anyway? Most people will probably know the answer to this question, so I'll keep it rather brief on the explanation. Iridium is a low Earth orbiting constellation of L-band communication satellites providing voice and data to the entire surface of Earth. One might think that SpaceX's Starlink constellation was the first to pioneer this technology. Iridium was the original low Earth orbit communication satellite constellation, and it dates all the way back to the 1990s, believe it or not. The recent rise of other low Earth orbit satellite constellations, such as Starlink and OneWeb, have greatly reduced the amount of traffic on Iridium. But here in Australia, Iridium is still very much in use due to our country's insanely large size and very sparse population. Most of Australia has little to no communication infrastructure outside the coastal population centres, therefore satellite communication remains an essential service for its rural and regional population. At the time of recording this video, there are large amounts of useful data that can be pulled off these satellites using relatively cheap hardware and a couple of free software tools. An Iridium satellite vehicle orbits our planet at an altitude of 780 kilometers, which means one satellite can cover a radius of about 4,000 kilometers. This 4,000 kilometer radius is broken up into 48 smaller spot beams, which each have a radius of roughly 400 kilometers. Depending on the quality and performance of your radio receiving equipment and how good your antenna placement is, for example, your antenna is mounted high up with a clear view of the sky, not obstructed by buildings or trees. And you should be able to receive data from Iridium satellites from an extremely wide radius around your location. Hundreds of kilometers potentially, and maybe 1,000 or more. And it's because of this ability to receive the communication signals from an extremely wide area, this is a good opportunity to delve into legalities and disclaimers. There's plenty of unencrypted public data which can be decoded on Iridium, such as date, time, location, altitude of its satellites, cellular control channel data, and ACARS messaging to aircraft, and there's others. But there's also an overwhelming amount of private data flowing across the Iridium network, such as voice calls, SMS, and pager messages, to name a few. I cannot and will not condone the use of this video tutorial for malicious purposes, such as intercepting private telecommunications being transmitted over satellite systems. Should you choose to disregard this warning and use my video for malicious purposes, I cannot and will not be held accountable for any legal trouble you get yourself into. Wiretapping laws in most countries are very strict and strongly enforced. The penalties are harsh and often result in jail time and or fines of very, very large sums of money. If you value your freedom, do not ever follow this tutorial. This thing here is the best method of experimenting with Iridium voice and SMS decoding. This is my old Iridium satellite phone, which I purchased secondhand for about 350 Australian dollars. I purchased a prepaid Iridium SIM card and sent myself a bunch of text messages and called it from my smartphone. And I recorded that traffic to play around with. Intercepting your own data flying over a telecommunication system is perfectly legal in most jurisdictions as long as that data originated from you or was intended for you. With all that being said, let's talk about the hardware requirements now. Us amateur radio operators will often say that the most important item in a well-performing radio system is the antenna. So the first item you will need in order to follow this tutorial is the RTL blog active L-band patch antenna V2. The V2 has the grey enclosure. V1 has like a black, dark blue. I'm colorblind, so I don't know what color it is. I think it's dark blue anyway. Aside from having the longest name ever, these things perform extremely well for receiving Iridium signals. It has inbuilt filtering and amplification, and it also doesn't need external power as it is powered by the bias T voltage of the SDR. We'll talk about bias T voltages later on, don't worry. The RTL SDR L-band antenna ships with a 3 meter length of low quality coaxial cable, or coax as us ham radio operators like to call it. This is how you will connect the antenna to the software defined radio. For this tutorial, I'll actually be using a 5 meter length of LCU 195 cable terminated with SMA male connectors. This isn't essential, but the higher quality coax you use, the better your recording of Iridium data will be, and your receiving system will perform a lot better. So yeah, I've upgraded my setup with some LCU 195 coaxial cable, which is the Australian equivalent of the Times microwave LMR 195 in America. The US, sorry. Now the second item we require for this tutorial is a software-defined radio. An SDR is the radio equipment that we will use to interface with the Iridium satellites and capture the data that is being transmitted by them. In this video, I'll be using an AirSpy R2. It is said by some people involved in the L-band satellite community that the AirSpy R2 is the best performing software-defined radio for capturing Iridium signals. Other SDRs that I have personally tested with Iridium decoding are the Hack RF, Blade RF 2.0, and the RTL SDR. I personally would avoid using an RTL SDR as these devices are only capable of capturing about 2.4 megahertz of the spectrum at any one time, whereas other SDRs I listed can capture the entire 8 megahertz bandwidth roughly used by the Iridium satellites. For an explanation on SDR bandwidths and how it relates to capturing radio signals, please check out this video of mine from the timestamp of 4 minutes and 12 seconds roughly. And the final thing I'll mention, it really should just be an assumption at this point, but for the sake of completeness, I will say that we need a working PC and an internet connection is not required for this tutorial. Let's talk about the software requirements needed for Iridium decoding now. The first one we need is Linux, more specifically Dragon OS Focal X. I highly recommend installing this internally and natively on your PC's hard drive, or running it from a bootable USB drive like what I'm doing in this video is acceptable. Iridium decoding does work in a virtual machine, but the performance overhead of virtualization and USB pass-through can and will cause issues eventually. It's also possible to download the Iridium decoding tools gr-iridium and Iridium-toolkit and their dependencies such as gnu-radio. But building and installing these from scratch in Linux is an absolute nightmare. DragonOS Focal X contains all the software tools you will need to follow this tutorial. So I always recommend just using this. It's the easiest way to get on the air without spending 3 days in the terminal trying to get stuff working. The next example of software we need is entirely optional. The Iridium decoding tools can output a couple of KML files, which can be opened in Google Earth. I guess that most people are just here for the voice decoding anyway, so you probably won't need this. Okay, first, before we can begin capturing Iridium data, we need to do a bit of configuration by editing some config files. gr-iridium is the first software tool we are going to configure. gr-iridium is the first stage in a two-stage process of decoding Iridium data. Basically how it works is it detects any Iridium burst signals that are entering the antenna. It demodulates them in software and finally writes the decoded burst to a file in your home directory. In order to configure gr-iridium, we will need to open a terminal window, which I've done already, and I'll go ahead and copy and paste this command. So some explanation is required for this. I'm using an AirSpy software-defined radio for this video. As you can see here, I'm editing the airspy.conf file in the example folder of the program files of gr-iridium. This is the examples folder here. And as you can see here, there's a list of supported SDR devices. So make sure that you guys are editing the correct configuration file for whichever SDR you are using. So I'll just hit enter on that. And don't forget to enter your password if prompted. And we can edit the config file from inside our terminal window. So the line that we need to modify is this one that begins with device arguments. Okay, so this is the point where we need to talk about bias T voltage. A bias T is the circuit inside some software-defined radios, but not all, that provides electricity through its RF port. Through the RF port and then through the coaxial cable for the purposes of powering a low noise amplifier, active antenna, or other inline devices that need electricity. The voltage supplied is about 4.5 volts at a relatively low current, something like 250 milliamps, around there. This diagram here is a simple bias T circuit, and we can see the positive and negative terminals here, with an RF only port at the rear, and at the front we have an RF and DC output port at the front. The RTO-SDR L-band antenna I'm using for this tutorial needs to be powered by the bias T voltage from my AirSpy SDR. If you are not using the same antenna that I am, you'll have to confirm whether or not your active type antenna is powered externally with its own power cable or requires power from the bias T of your SDR. If your antenna is a passive type antenna, you won't need any electricity to power it at all. Please double check and then triple check whether or not you need to change the following setting, because I won't be held responsible for any damage you do to your equipment because you sent a voltage somewhere it shouldn't have been. So back to our terminal window now. The first thing we need to do is uncomment the line by removing the hash symbol. So I'll just go ahead and do that. And where the text says bias equals, we need to confirm that the number 1 has been configured. And as we can see here, it has been by default. So 0 means bias T off and 1 means bias T on. So once we've configured that, we will press the Control X key. We will press the Y key on our keyboard. And then finally, we press the Enter key to save the document. So this configuration file will now instruct gr-iridium to turn on the bias T voltage of the SDR and power my active antenna. I've actually got 2 of these, so I've got one outside already configured, ready to go. So this is just my second one I'm using for the purposes of showing you guys the antenna. Okay, that's all we need to do on the gr-iridium side now. Next, we need to configure Iridium-toolkit. So anybody who has played around with Iridium decoding in the past has probably encountered this error before. Play Iridium ambi not found. This is a problem caused by Linux not knowing where the play Iridium ambi bash script is located, and it will throw this error in the terminal window when we try to replay Iridium voice transmissions. We can rectify this by adding the path to the Iridium-toolkit programs file on our bash rc file. Now, it's a bit of a mouthful, I understand, but just please follow along with me. So in the terminal window now, we'll turn our attention back to it, and I'll copy and paste the following command. And don't forget that I'll put all the commands that I run in the description to this video and probably in the top pinned comment. So I'll just hit enter on that. And this will open a text editor inside our terminal window once again. And we need to navigate to the very bottom of the file. So I'll just press down, the down key on my keyboard, and we'll go right to the end of the document. And then we need to add this line here to the very bottom of the document. So I'll just copy and paste that. So yeah, emulate this exact thing that I'm doing here. And then again, to quit the text editor, we will press Control X. Oops, sorry, Control X. We press Y on the keyboard and then Enter key. Now this next step is very important. In order for the changes we made to become active, we need to quit our terminal window and then relaunch it. So I'll go ahead and do that, and we can move on to the practical segment of the tutorial, finally. So yeah, quit the terminal window, relaunch it, and then the previous changes we made will now become active. So I'll just set the scene hardware-wise now. It's too hot outside to give you guys a grand tour of my Iridium decoding setup. So you will just have to look at this awesome Microsoft Paint image that I made. So essentially I have my PC powered on and booted into Dragon OS Linux. I have my L-band antenna sitting on top of my outdoor shed. It's about 3 meters off the ground with a clear view of the sky. The coaxial cable is attached to the RF port of my antenna and to the software-defined radio. My SDR is plugged into the PC with a USB cable. And here's an image of my antenna sitting on top of my garden shed. It's quite high off the ground with nothing but blue sky and clouds above it. If you place your antenna very low to the ground, where its view of the sky is obstructed by trees or man-made structures like buildings and houses, don't expect to capture any usable data from Iridium satellites. So we'll turn our attention to the terminal window again, and I just browse to my home directory in the file browser. The first command I'll run is the one that will confirm that our SDR is visible and available to Linux, and that the driver modules have been loaded correctly. So I'll just copy and paste this next command and hit enter. Sorry, that didn't work. And I'll just press enter on that. And we can see here that it is immediately apparent that my S by R2 is being detected by Linux, and it's ready to capture some Iridium data. So I'll just clear the terminal window So basically now, I'll proceed to copy and paste the following command. And this command is going to instruct gr-iridium to tune my software-defined radio into about 1.6 gigahertz roughly, and start recording Iridium data frames to a file in my home directory. So I'll just hit enter on that. And you'll immediately see a file being created inside my home directory titled output.bits. And the terminal window is beginning to populate with various pieces of information in the output. As time progresses, the output.bits file will grow larger in file size, as we can see here. This is indicative that Iridium data is being demodulated and written to this file. So far everything is working as it should be. Excellent. So I'll just take a moment to explain some of gr-iridium's terminal output now. So all these values you see here are just as important as each other. However, in my experience, and this is only my experience, I'm not an expert, this is just real world lived experience, I've narrowed down 2 columns of information which will indicate if you have a well-functioning Iridium ground station. So highlighted in green here, these values are indicating how many Iridium data bursts are being detected per second. These numbers will vary wildly as time progresses. If there are Iridium satellites passing directly overhead of your antenna, you should be seeing values of several hundred up to 1,000 or more. But not always though. Depends on how much traffic is flowing over the satellites and if anybody in range of your antenna is using Iridium at that moment. If the Iridium satellites are not passing directly over your antenna, you should be seeing values of a few tens or more, such as what is happening with my setup currently. This is completely normal, don't worry, don't stress about that. Most important thing is if you see the file size of output.bits rising, that means you're getting data. So don't stress. Highlighted in blue, we have the average percentage of frames that have been successfully demodulated and written to output.bits file in our home directory. Obviously, a higher percentage is desirable. That means this means more data has been captured from the satellites. Using these 2 columns of data in the green and blue boxes, we can determine if our Iridium receiving setup is functioning nominally. If you have a consistently high number of bursts being detected, that's the green column here, but your average percentage of OK frames is very low, maybe it's in the 5%, 10%, 15%, this means that your setup is performing very poorly. This could be caused due to man-made RF interference or electrical noise from AC power cables. You'll have to rectify this issue by moving your antenna and SDR away from the suspected source of the interference or electrical noise. And yeah, we'll just read this text in the red down here. If you have a very high number of bursts being detected, but a very low average of OK frames, there's a problem with your setup. Okay, let's talk about duration now, or how long you will need to leave gr-iridium running in order to get decodable data stored onto your PC. I've had a few people emailing me complaining that they weren't observing any Iridium data at all, or only got very small amounts of it. And the cause of this was that they were only running gr-iridium for a few minutes. As a bare minimum, I recommend running gr-iridium for 2 hours or more. Capturing for 12 or 24 hours would be even better. Remember I said before that Iridium traffic has drastically reduced since the introduction of Starlink? You will capture exactly 0 data if you run gr-iridium for a few minutes. Running it for as many hours as practically possible is a sure way to ensure that you will have data to decode at the end of the day. Anyway, I think this video has overstayed its welcome at this point. So what I might do is split this tutorial up into 2 separate parts. So this will conclude the first part for today, where we covered the hardware and software needed for Iridium decoding. and we demonstrated the usage of gr-iridium. Keep an eye out for part 2 in the coming days, or maybe next week. I'm not really sure at this point, but when it does drop on my channel, we will be covering the usage of Iridium-toolkit and its role in the extraction of usable data from an Iridium capture file, which is this output.bits file here. So yeah, I'm just going to quit the capturing application now, and I'll say thank you very much for watching, and I'll say goodbye also. Cheers.